so information for you about these patterns in Helimagnets, but at the very end, if time allows, there will also be some, at least mathematical connections to these models for shape memory alloys. I mean, scalar models for shape memory alloys that you might know from, for example, the works of Kohn-Müller in the 90s. So the starting point for our analysis is the following work by Marco Chiralities and co-workers in his group in Munich, which is the following. So you have a lattice spacing epsilon, and then you take a square lattice with this lattice spacing, and you consider spin fields or just unit vector fields on this lattice. And to such a spin, you assign an energy which has the following form, sometimes referred to as the J1 or J3 model. Has two contributions. So the first one is an interaction with your nearest neighbor in the grid. The second one is an interaction with, say, your second neighbors in this grid. So yeah, or I didn't write here, but so I should refer to them as second neighbors. So the next nearest neighbors normally should be the diagonals. And okay, so there's a competition between the two guys because so the nearest neighbor interaction comes with a negative prefactor, which means that in order to minimize the energy, you have a certain spin at this purple dot. Then the green guys, your nearest neighbor, would like to be aligned with you. Okay, purple. On the other hand, your second neighbors, they would like to be aligned with you. However, at the same time, of course, they're nearest neighbor of the green guys, so, well, they don't really know what to do. And there's a competition between those effects, of course. And so what Marco and Francesco did is they, in 1D, but because the whole thing, as we wrote it, is just essentially two 1D versions along rows and columns, so it kind of decouples. So they studied this in 1D. And they found out that, say, the minimizers of such an energy look as follows. If alpha is big enough, then the second contribution is somewhat simply suppressed in the sense that minimal configurations are simply completely aligned configurations. If alpha is smaller, then there's a compromise between the guys, and the compromise is that your spin field starts simply rotating with a certain optimal angle, either clockwise or counterclockwise. Okay. And the optimal angle here is given by this expression, which at least passes the simple reality check that as alpha goes to 4, this goes to 1, so the R cost should go to 0. So they rotate less and less. So that sounds not too bad, and those are just pictures of those 4 configurations that we now have in 2D, because you can have rotations clockwise or counterclockwise in rows and columns, and combine them. And now what we'd be interested in would be the transitioning regime as alpha goes to 4 from below. So they might maybe things happen. We write that in the way that alpha is given by 4 times 1 minus delta, and delta goes to 0, and we'll, essentially from now on, forget the alpha and simply have this delta. Okay, and so because you know these minimizers so very explicitly, what Marco could do is to really kind of rewrite the energy minus its minimum in the following way, where you just have these sums over certain squares. And so now we take one of those terms here, say the first one, multiply it with epsilon squared, and massage it a little bit, and try to convince you that it's close to a certain continuum model. Okay. And yeah, so we start with this guy here. Then we plug in what alpha is. So alpha is 4 times 1 minus delta. 4 over 2 is 2. 4 delta over 2 is 2 delta. So that's here. And then this first guy here, looks essentially like a second derivative up to a scaling factor of epsilon squared. You plug this in, you expand the square, and you replace epsilon squared times the sum by an integral. Very good. So what we have here is now this expanded square. So the second derivative here, there's this term that sits here. We call that use a unit vector field, so there's no 1, and then there's a mixed term. Okay. So the mixed term now, depends on how you want to argue. So let's say use a unit vector field, which means that, okay, so the norm of u is constant. You take one derivative, you get that u times, well, u dot del 1u is 0. Take a second derivative of that, you get that u times the second derivative of u is minus the first derivative of u squared. Plug this in, rearrange things a little bit by by lifting everything in terms of an angle function. So now you write u in terms of an angle function psi. And then, of course, you get first derivatives of u simply translated to first derivative of the angle function. Second derivatives of u, you get product rule, essentially, but the two terms are orthogonal to each other, so you simply just get two terms. One is the second derivative of psi, and the other one is 2 second derivatives squared, so it's a fourth power 4 of the first derivative psi. Okay, essentially done. Now you take this last three terms, so for me it's always easier to go from here to there. So this is also perfect squared. In the sense that, yeah, it looks like this, and you can check. So some of this term squared sits here, this term squared sits here. This is the mixed term. Okay. And now the last thing to do is just to rescale the function psi in such a way that this should be an order 1 quantity. Okay. So essentially, you do that brutally, some way. Doesn't matter how it looks exactly. So the point is that after rescaling and introducing a new variable or a new parameter which depends somehow on epsilon and delta, you realize that the energy minus its minimum looks up to a factor which depends on epsilon and delta, looks like this kind of continuum model, where you simply force the so the x and the y derivative of your rescaled field phi to be plus or minus 1, and you penalize transitions between these different states, essentially. And so also, if you compute everything back, then the x or y derivative of phi being plus or minus 1 corresponds exactly to the situations where the original spin field rotated clockwise or counterclockwise with the optimal angle. This is the picture of the 4 different states again. And then, so what Marvin Koser and Orlando did is they essentially looked at this energy, they rescaled it, so you saw this parameter, and then looked at the limit as sigma goes to 0. And I mean, you allow me to oversimplify this a little bit, then essentially what happens is you get a modica modular type result, which, okay, first glance should not exactly be true because you're looking at gradients and I mean higher order things, but I mean it decouples into essentially one-dimensional versions of modica modular, and there it doesn't really matter whether you're a gradient or not. Okay, so what you should get is that the limit as sigma goes to 0 of such a thing, well, is only finite if the derivatives of phi are plus and minus 1, and the limiting energy is a sharp interface limit, so you should simply penalize transitions between the different states that are known. And so we are interested in something slightly different. So we'd like to assign, say, boundary values to the spin field, say the discrete, and then study the behavior of this model in terms of scaling laws with respect to the parameters in the game, which would be epsilon delta. And they, as we'll see, will not essentially allow, they are in a different energy regime than the energy regime that was considered here to some extent. So the first thing that we did with Melanie is written, but not for the public eye yet, is that these heuristics you can make rigorous in terms of gamma convergence, including boundary values for phi or vice versa, the spin field. Okay, so it means that what I'm going to do from now on will be to look at this continuous energy and want to study essentially its behavior with respect to the parameter sigma. Parameter sigma and a second parameter that we bring in through the boundary conditions. So we restrict ourselves to the unit q. Sigma is here positive. The theta is a parameter that moderates the boundary conditions. So what we do is we simply take the left, so for you it's like this, the left side of the square and assign to it boundary conditions which are linear, but say the y derivative of the boundary conditions is incompatible with just one. I mean, it's not exactly 1 or minus 1, but it's a correct combination of the two. So the smaller theta, the more compatible somewhat the boundary conditions should be to just using one gradient out of the 4 people. All right, now I'll switch things just slightly. Okay, so that would be, so we'd like to understand that. Instead, we look at a slightly different function, essentially just because it's a little bit easier to treat mathematically, but everything that we prove for this one, essentially, you can translate for this guy here as well. So these two terms here, they essentially want the derivatives of phi to be plus or minus 1 in each component. This we replace by simply a distance to the set of 4 preferred gradients. Of course, there's slightly different growth, but will not matter in terms of scaling laws. And then these terms here, of course they don't allow for sharp sharp transitions, and we replace them essentially by a total variation type term where you simply have to account for the surfaces created between the different regions. Okay, of course, then if you can prove something in terms of the scaling law for this model, you can kind of bring it back over here by modifying on the right scale. It should be right. And okay, so of course the one thing that that might be critical is that I also replaced just say the x-x and the y-y derivative by a full Hessian. Okay, there you have to believe me, I will not show it. But so if you look very closely into the proof of the lower bound, you will see that you essentially only need those terms and not the full Hessian. This is just all right. And okay, I think I've essentially already said that I mean the boundary conditions are made such that they're incompatible with just one of the 4 preferred gradients. And this might lead to, at least if sigma is very small, so if transitions are between the different preferred gradients are cheap, it should be expected to some degree that you want to achieve the boundary conditions by essentially high oscillations between y derivative plus 1 and minus 1 close to the boundary, so in order to weakly converge to, say, slope 1 minus 2 theta close to the boundary. Okay. And so we'll try to prove that in terms of the scaling law, which simply means that we want to find an expression depending on sigma and theta, such that up to multiplicative constants, which might be different, the minimal energy here behaves like this expression. And in order to do that, of course, you have to do two things. For the upper bound, you have to come up with an appropriate competitor, which essentially gives you the optimal scaling, and then you have to prove an non-discrete lower bound. So before we really dive in, let me just briefly mention that, of course, the model that we have here lies in between two very well-known and well-studied things. So the first one would be, say, 2 gradients, which would more or less, I mean, slightly different here, but say you replace K by this guy, only the set where this guy and this guy is in. And this was, for example, studied by Kohn-Müller and then many more people, of course, later. And it gives you a certain energy scaling, which of course now for us gives us an upper bound. And then there's of course also something like a Giga, where you have a whole circle of gradients available, which is in this situation completely boring because the boundary conditions are such that they're completely compatible, so it doesn't tell you anything. And what we'll see is that so the minimal energy in our setting here, where you have 4 preferred gradients, will be either that one that's to be expected, but also will be a lot lower than what's given here in the two gradient setting. Okay, so here's somewhat the warm-up version. So this is now theta being equal to 0, so equal volume fractions for y derivative plus 1 and minus 1, and this means 0 boundary conditions. So just to get an idea, essentially you can do the heuristical argument that you are you should expect to be in either one of 2 extreme cases. So the first extreme case is that you'd like to be your gradient really to be in the set of 4 preferred gradients more or less all the time. And this will tell you the following, that, okay, so that your your x derivative has modulus 1, which means that if you start from the boundary, here you're 0, you go into your domain, your x derivative is bounded by 1, so you're something like bounded by x if you go x far into the domain. However, at the same time, so if you now look at such a vertical piece, at the same time your y derivative there is also bounded, is also plus or minus 1, but you have to be small at the same time. So you can try to achieve that by forming these kind of zigzag patterns in the vertical direction, and then you have to have a certain number of jumps, which goes like 1 over x essentially. On the other hand, the other extreme case is of course that, say, sigma is large or whatever, so you don't want to have any transitions between the 4 preferred states, so you kind of have to be what the boundary conditions dictate you to do, and this of course produces an order 1 energy in this first term here. Okay. And now you can get a naive lower bound using that, in the sense that you simply look at all those vertical slices here, and you integrate up the energy contribution of the two, which is smaller. Okay, so which means that your energy could be bounded below by such an integral, and if you compute this, what you get out is a term which looks like sigma log sigma, or order 1 if sigma is too large. And this is exactly what in this situation should be the optimal scaling result. Yeah, so the minimal energy behaves exactly like sigma log sigma, or 1, depending on which one of the two is smaller. And so of course the order 1 term here is in some sense the boring guy. I mean, this essentially corresponds to just uniform, I mean, to competitive or to phi's, which are just, for example, 0 all the time. So they achieve the boundary conditions in a boring way, and those should kind of correspond to some patterns forming. Okay. Right. So yeah. So I hope that I kind of at least theoretically convinced you that this could be a good lower bound. So let's now talk about competitors very quickly. Yeah, as I said, so the first one is simple. If sigma is large, you want to be something like order 1, so you just put phi equal to 0. And now, yeah, now your sigma is small, so transitions are allowed, and so the heuristics are that if you're x far into your domain, you should have something like 1 over x jumps in your y derivative. And essentially we mimic that in the way that we construct a certain building block, and then construct a gradient in a self-similar way, so that it refines towards the boundary following this law, roughly speaking. Okay. And of course, I mean, so the good thing is that because we have a scalar phi, I mean, all the 4 different gradients are compatible along a rank 1 connection, and yeah, so the corresponding surfaces are just diagonals, horizontals, or vertical lines. Okay, so there's not so much that you can try to do, and the good thing is there are not things that you try first. So you start with 1 jump in the y derivative here, and you refine to essentially 2 guys which have 1 jump in the y derivative each and are half the size. Okay, and this you use as a building block. You put it here, then you take it, you isotropically rescale it, and you glue it next to each other. Okay, and what this gives you is an energy of the form where you now have to. Okay, so you're within the set of preferred gradients all the time, so you just have to count interfaces here in order to compute the energy, and so the amount of energy or interfaces that you get is of order 1 over length 1. So this should give you, for each of those construction steps here, so for each refinement step, if you want, you get an energy which is of order sigma, so you get the sigma times n, and this means you can't do that forever. At some point you have to stop, and you have to interpolate to the boundary in some way, and this gives you an energy which decays exponentially. Now you optimize in n, and what you find is, it was already exported before, I mean, what you find is the optimal. Okay, so now there's a slightly different perspective on essentially exactly the same thing, slightly different construction. So if you start, so again, these colors, they simply encode the 4 preferred states, and so this large inner block here corresponds to configuration of a gradient whose primitive can be chosen in a way such that it's 0 along those boundaries here. And then essentially proving the existence of a good competitor boils down to using this as a building block and rescaling this guy and translating it around, and essentially just finding a good and relatively simple covering of the domain that you're looking at, and then you just have to count in order to compute the energy. You just have to count surfaces created versus area left, okay. And this gives you exactly the same optimization problem as before, and then of course obviously also the same energy scale. All right, but of course, so if you do it this way, then you see immediately that it doesn't matter whether you put 0 boundary conditions here or everywhere. It all gives you the same scaling law. And of course, you can also now send this construction to infinity, and you'll get a solution to the differential inclusion. So meaning a function which is Dirichlet, the gradient is within the set of preferred gradients almost everywhere, and there's 0 boundary conditions on the sides of the square. And then by interpolation, you can prove it has a certain regularity which is below BV, because I mean BV you cannot have because of the scaling law that we proved. So this is this, and this picture is essentially the construction from before, but say cut out this part and they're mirrored in the three different other parts of the domain. So you see the pictures are roughly speaking the same. So now let's see. Here's the general case for where we bring back the theta. And okay, so before we did theta equal to 1/2, and okay, now you can try to play the same game as before. So this heuristics, and what the heuristics tell you is that yeah, you leave the boundary, you go into your domain. Now again, you look at this such a vertical stripe. You should have a certain number of jumps in the y derivative, and this is something like theta over x instead of 1 over x as before. If you believe that your gradient is always within the set of preferred gradients. Okay, and on the other hand, of course, the other extreme case was that your y derivative does essentially what the boundary values dictated to do, and this in this situation gives you an energy which is of order theta squared. Okay, you again try to use this as a lower bound, and yeah, you get out a certain expression which is down here. I mean, maybe you already hear in the way that I'm telling you that, as you can do that, but it will not give you the optimal thing, and I'm trying to convince you why it's a little bit more difficult, I mean, a little bit more complex in this situation. So first we saw that, and we thought, okay, let's try to mimic that again, simply by a certain construction. So the naive way of doing, yeah?
Question. So you're breaking the symmetry with theta. So are you able to identify the base fractions of the 4 gradients in these constructions which follow? Are they?
Yeah, sorry. So the theta. Yeah, so this is just so it's slightly different written than normally, but so this is just convex combination which corresponds to 1 minus theta volume fraction of y derivative plus 1 and theta negative 1, and then you're essentially free to. I mean, they essentially in this sense work the same way, and those two also work.
I guess what I meant was it's a boundary condition. It's not a bulk condition.
Yeah, the boundary condition.
So in that sense, the bulk distribution of gradients, is that not partly free?
Yeah, essentially. I mean, I'm not so sure if I understand the question correctly, but I think so. So it's just a condition here, right? So it's a condition which only, roughly speaking, only applies very close to that boundary. And there's no condition on those boundaries here, so you don't have to have the right volume fractions here. I mean, if you wanted to, you could also put boundary conditions here and there, such that they fix the volume fractions in here as well. If you wanted to, I'd be willing to claim that it should work the same way. Right, so the naive version of the construction from before is the following. You start with the correct volume fractions, so -1 here is a relatively small fraction, +1 here is relatively large, and you refine this one jump of the y derivative to 2 blocks with 1 jump each in this way. And because theta is small, you don't have to change too much, which means that this length scale here is relatively short. And then for the energy, you just look at the surfaces created as like order 1 number of surfaces, so your surface energy in such a building block should be like theta times sigma, okay, for each of those steps. It's already here. Okay, so sorry. And then you would try to use that, put it here, and use it again as a building block in the same similar way as before. And then you realize, oops, by gluing them together, you create a lot of surface energy on those vertical lines here. Which is not, I mean, yeah, in some sense you don't see in each building block alone, but if you glue them, you'll see it. And this is of order 1 for each of those blocks, which means that essentially from the x derivative, you pick up a sigma times n if you do n steps, whereas the other one is just n times sigma theta, where this will be the correct one if you believe in something like this. But the problem is, I mean, then of course you try to improve it somewhat, but you can't get away. You cannot take one jump of the y derivative and try to refine it into more without creating jumps in the x derivatives if you want to stay within the set of 4 preferred gradients. So and then after some time you realize, okay, the best thing to do is to balance the 2 terms by creating more horizontal or more jumps in the y derivative in each building block. Because I mean, in some sense, for each block, anyway, you have to spend such an amount by gluing them, then why not spend it here as well? Relatively straightforward, but got a little bit of time to figure out actually. So And that's what we do. So here's the sketch for theta being equal to 1 over 3. So you start with one jump here, and you refine into 3 blocks with 1 jump of the y derivative each. And this now has exactly the right properties, in the sense that now if you look at all the surfaces created here, this is the width here is still roughly something like theta, but you create, roughly speaking, 1 over theta many interfaces. So this is in order one energy in terms of the interfaces times sigma. So this exactly balances what you anyway get from doing these things together. Okay. And maybe I should also say that. So so here's theta. So the first building block goes from theta to theta squared, and you refine exactly now. At these vertical lines here at the end of the building blocks, you get exactly the behavior that comes out from the heuristic computation. So here you have theta over x many jumps, namely 1, and here you have 1 over theta many jumps, which is again theta over x many. But in between, you violate this condition heavily, and well, it's a good indicator again that what you did, if this is in any way optimal, then the computation from before was definitely suboptimal, because it completely underestimates what you're doing within such a building block. Okay. But then, of course, the name of the game is the same. You have an optimization problem, the number of steps that you do. Your interpolation layer decays a lot faster because you introduce so many more. So you refine in a much faster way than before. So it decays at this rate, and then you optimize in n, and what you get out is the following expression here, which is a sigma log sigma. So this essentially looks like before. However, the theta term does not appear here as a prefactor, but instead it comes in the denominator as a logarithmic term as well. And then just one more picture for the construction. So theta equal to 1 over 3 is of course a little bit cheated in the sense that 1 over theta is a natural number, and then you can draw these pictures quite nicely. If it's not, then it looks a little bit more messy, but you can essentially do the same construction with the same idea, you just have to round up. All right, and so then this is the corresponding scaling law. So you prove essentially that this is the competitor that I just tried to construct in some way. Then, of course, there's also the competitor which just comes from the boundary conditions again. So this is the theta squared. Okay. And then you have to prove a corresponding lower bound. And on the next slide, I'll just have a very short sketch, which is also just essentially there to convince you of the fact that balancing the XX and the YY contributions is the right thing. Okay. In order to do that, I always need this reminder for myself. So if sigma is in between theta to the k plus 1, theta to the k, then this term is essentially just k, right? But I need this reminder always. So we take such a sigma, and then what we have to prove is that the minimal energy is up to a constant larger than k times sigma. And now we do, roughly speaking, exactly what we did in the upper bound construction. So it's, we really kind of mimic this behavior in the lower bound construction. So you take those points, the xi, which are like theta to the I, and these are essentially the endpoints of the building block steps. So you choose those guys such that they are more or less representative for a certain region around them. Okay, so those are the xi's here, and the actual theta to the power i's, they sit somewhere here, and maybe here, the next one, and so on. Okay. And so now what you have to prove is that this expression here is larger or equal sigma, which if you sum those up, you get exactly the k if you do k points here. Ignore that for a second. So now the argument is relatively simple. So you subdivide your vertical slices into intervals which have also the same length scale, so something like theta to the power I. Okay, why is that? If on each of those, so in our upper bound construction, it would be expected that on each of those guys here, the y derivative would jump once. Okay, so you'd pick up an energy contribution which is of order sigma for each of those intervals. And then, of course, you have theta to the minus I many of those, which would mean this here is bounded below by C. Okay, so if you have a jump in the y derivative, that's fine. You should get good lower bounds. If you are somewhat violating the fact that you should be one of the preferred gradients, so if your y derivative deviates from plus or minus 1 in a somewhat significant way, this should also give you good lower bounds. And if both of those things are not the case, then roughly speaking, so you are close, somewhere you're close to y derivative plus 1 or minus 1, and you're not allowed to leave that really far. So essentially on the whole interval, you're close to a fixed y derivative theorem plus or minus 1. And this means that you're essentially fine here. On the other hand, if you compare with this guy, it's already a lot closer to the boundary, which means that more or less you can replace it by the boundary conditions. And so then you have something here which has say slope 1 or minus 1. Here you have something which has slope 1 minus theta. And this means that you can find a lot of points here such that on those horizontal lines, connecting those dotted lines, you have a difference quotient which is not really plus 1 or minus 1. And if you have that, then you can play now the same game horizontally. So if this is true, then you can do two things. Either you want to stick with x derivative being plus 1 or minus 1, but then you have to have a jump in the x derivatives because you can't use one of the two the whole time. Or you leave the realm of having x derivative plus 1 or minus 1 exactly, and then you also produce a certain amount of energy in the non-surface term of the energy. So this should give good lower bounds on these horizontal lines, which would mean that this energy, so the energy between those two guys here, would be relatively large, or would be large enough. Let's put it like this, and then so if you can bound this or that is essentially the same. You add it up and you get your lower bound. All right. So more pictures. This is essentially just the construction that I showed you before, and the same thing happened. I cut out this part here and I mirrored it in the different directions such that you can see that you can, for example, achieve also boundary values all over your square, which correspond to those boundary conditions. I'm not so sure if I ever said that in the very beginning, but I should have said it. So zero boundary conditions, of course, if you translate everything back to the spin field, zero boundary conditions correspond to a non-moving spin field on the left of your boundary. Those boundary conditions here correspond to a spin field that rotates on the boundary, but slower than the optimal rate should be. So which means that you have to essentially achieve that by rotating the same way and then rotating back a little. I mean, rotating optimally one way and then rotating optimally the other way. So those corresponds to those patterns that you see. Okay. So then, in the last, the remaining time, let me just draw some connections to those two gradient models. So if we go back to the very beginning. Go very back to the discrete model. There was this prefactor alpha, right? And this, which was the prefactor for the nearest neighbor interaction of the spins. And so this prefactor was essentially chosen the same for the rows and the columns. But of course, you can use different ones for the rows and the columns. You can plug everything in, you do the gamma convergence result, you end up with an energy which has the same form, up to the fact that the set of preferred gradients is now not plus minus 1 in each component, but for example, say plus minus 1 in the second component, plus minus gamma in the first component. Which just means you brought in one more parameter to the game, and you can try to do the same thing. You can try to prove scaling laws now with respect to those three parameters. Again, so we did that, but again, hopefully now the lectures are over, you might be able to see it soon. Right, I would just try to mention two things, essentially. So if gamma becomes very small, what happens here is, of course, that your set of 4 preferred gradients simply collapses to a set of 2 preferred, collapses like this, so to a set of 2 preferred gradients. So you're essentially back to the model which has 2 preferred gradients for which construction, scaling laws, and so on are very well known. On the other hand, you have the same effect actually for gamma being very large, because then you have 4 preferred gradients sitting here and there, the vertical distance between two of those guys is something like 1, but the horizontal distance is huge. It's like 2 gamma or something. And then this means that essentially it doesn't make any sense to transition between those which are very far apart. So you just have to decide and stick to 2 of them. So you're back at the 2 gradient problem essentially. And so this is a picture. Okay, now let me maybe stop here. So this is a picture which is from the upper bound constructions in some of those regimes, where essentially you do the same thing that we did before. So if you see here, these cells here, before they were simply rotated normal squares. Now they are compressed because of the fact that the x derivative is very small. So we're talking about gamma being very small. And then you try to use them again as a building block and essentially build with them a competitor the same way as before. Then there's this picture here, which is not exactly, but let's say a version of what was constructed by Kohn-Müller. So this, I should have said that. So sorry, this is all for equal volume fractions, right? So for theta being equal to 1/2. So it's essentially the same situation, but slightly different. So I mean, here the colors encoded the 4 preferred gradients. Here the colors simply encode the fact that your y derivative is plus or minus 1, because if, say, your x derivative is fixed, you can't do anything if you stay within that set. So you have to leave that anyway. So yeah, so the colors just encode the y derivative, and then you see here this is a building block which defines 1 jump in the y derivative to 2 blocks with 1 jump each. And then again, you use this as a building block, but in a different way, because here we kind of isotropically rescale the building blocks in a Kohn-Müller construction. This is non-isotropic done in a non-isotropic way, which I don't know if you can see that, which kind of leads to the visual effect that these lines, if you follow them, look slightly curved. But so here this is a straight line all the way to the interface. This one here looks slightly curved. Okay, and now really the competitors in the regime where gamma is very small look as you would naively hope. So if gamma is very small, this should be a good guy. If gamma is, say, moderately large, this should be a good guy. And in between, you start like this, and then at some point you transition, and this is here, you transition into this kind of construction, and to use this as an interpolation towards the boundary. And then really, depending on how large gamma is, either this one shifts over here, or this construction shifts over there. So, yeah, this is really, we prove this, I mean, rigorously in terms of scaling laws and corresponding lower bounds, but yeah, I mean, that's one regime. There are quite a few regimes with the 3 parameters. Kind of over this slide, so this is just the corresponding explanation. Okay, and then maybe some last words on what can you try to do for different domains. I mean, so far we talked about the unit square, and the question is, can you do more general domains? What would be nice. And the first starting point would be, for example, to take the square and rotate it, but keep the same set of preferred gradients, or alternatively, you start rotating your set of preferred gradients and keep the unit square as it was. So now I simply put 0 boundary conditions all over this rotated square, and there's a parameter which is called gamma, and this is simply the angle measuring the angle between say this line and this line, which means that if the angle is 0, this line and this line here completely agree, and everything's more or less completely compatible. Okay, so yeah, so morally, gamma being small should again correspond to having a high compatibility of the boundary conditions and the set of 4 preferred gradients. And then again, you can prove the corresponding scaling law, which looks roughly speaking the same way, in the sense that again you see something like sigma log sigma, and now in some sense the angle here simply replaces, so the angle also measuring the compatibility here replaces what was the theta before measuring the compatibilities also with boundary conditions the same way. I mean, to be honest, I mean, some of those things, it looks exactly the same, but some of the things are swallowed by the fact that you're working with logarithms, because you can't see any exponents down here. So it looks exactly the same way, but some things are different. Just if you don't write it explicitly, you don't see it, and it doesn't matter for the formula. Okay. So right, and then of course upper bound constructions you can do by exactly this perspective that I presented in the very beginning, that you take this as a building block. The grade is a gradient of a function which is 0 here, and now again it just boils down to covering now the rotated cube by those unit cells, or dilated and translated versions of this unit cell, and doing this optimization process of creating surface versus area left out. Okay, and I mean this way you do this in a not super clever but slightly different way than before. You get this kind of scaling law. Okay, and of course, I mean with this kind of construction, you can construct any kind of. I mean, you can construct competitors for a large class of domains, of course. However, I mean, I'd say that proving corresponding lower bounds, to me at least, seems not so easy, because I mean, somewhat to do with the geometry of the domain, somewhat plays a role in some way. Okay, and it's not so easy to quantify, like for this specific domain, with this, for example, this domain. Okay, so I guess with this, let me wrap up. So what we did is we considered this variational minimization problem that, at least heuristically, and you can also prove it rigorously, comes from a discrete spin system, and so there are, or it is expected that there are patterns forming close to the domain boundary due to incompatibilities of the set of preferred gradients and corresponding boundary conditions. And we study this in terms of the scaling law. And then, of course, in the future, there are things to do. So the first thing will be to kind of try to transfer the results that we have in the continuum now. I mean, we did this whole continuous approximation to learn something about the discrete. And of course, what we learned in the continuous setting, you can transfer to the discrete. However, there are more regimes appearing in the discrete, because there are situations apparently where the continuous approximation is not really valid. It corresponds essentially to, say, singularity or topological defects in the spin field. If you rotate around once on one of the unit cells, your approximation of gradients, if you lift everything, you put simply a gradient there, it's not really a good thing to do. And this, I mean, appears in certain regimes in the discrete, and we're currently trying to figure out what exactly happens. So what I can say for certain is that there are regimes where none of the scaling laws translate to the discrete from the continuous are not done, essentially. Okay. And then, of course, would be interesting to do different domains, or, for example, for mathematical purposes, to do just different sets of admissible gradients, less symmetries, more gradients, for example. Okay, so with this, let me thank you for your attention.